All right, if I may, to pick up sort of right where we left off last time, we were getting familiar with series, which are essentially sums of ordered collection of numbers, and we asked the question, hey, what if you had a sum of infinitely many numbers in an ordered collection? Could we determine the sum of such an object? Well, that's definitely an interesting question, and that's what's going to lead into this video. So, yeah, can we determine the sum of infinitely many numbers in an ordered collection? That might seem like a daunting task. I mentioned last time, and I'll say it again, I mean, if you give this task to an accountant, the first thing they may do is just start plugging the numbers in the calculator, like A1 plus A2 plus A3 plus A4 plus A5 plus, and so on and so on. And now, I don't know if you ever have seen such a device, but one of these calculators that has these tapes coming out of it that sort of keeps a running tally of what you're getting after each term is being added together. Well, you know, that's something that if the accountant was adding up the numbers, they would add up what the first number was, and then they'd add in the second number, and they'd get something as a result. They'd add in the third number, and they'd get something else as a result. Add in the fourth number, add in the fifth number, add in the nth number as they're adding in the numbers. And as you're adding up, you're getting essentially a running tally of what the sum is. So these S1, S2, S3 out to SNs here are essentially a running tally. Let me write that in here. A running tally, like a subtotal in effect, for what you're getting whenever you add up the first how many numbers. Well, that running tally, that subtotal of the first how many numbers, we're going to refer to as the nth partial sum. So when we say the nth partial sum, that's just going to be the sum of the first n numbers in our series. So in particular, like A1 plus A2 plus A3 would equal the third partial sum. It's just the sum of the first three numbers. It's what you get when you don't add up all the numbers, you just add up a part of the numbers, namely the first three. Well, now here's what, so a partial sum is cool, but you know, what does that have to do with adding up infinitely many numbers? Now, what it has to do with is it gives a concise way to talk about the sum of the first however many numbers. Because think about this, if you want to estimate this sum, or if you asked an accountant, let's say, to estimate the sum, what they might do is just hammer away on their calculator for a day or two or three, and after they get a million numbers into the sequence, they could tell you how much a million numbers added to, and that might be a pretty good estimate of what all the numbers added to. Right, if we use this partial sum notation, like what would S1000 be? Well, that would just be the sum of the first 1,000 numbers. So this would be like A1 added up out to A1000. That would be a decent estimate of the sum of all the numbers, because hell, there's a lot of numbers there. But, you know, adding up the first 1,000 is great, but hell, adding up the first million is even better. So if we could add up the first million, now we would get an even better estimate of all the numbers in the sum. But even this has to be, or almost certainly is, a little bit off. This is not great. I'd rather have an even better value. You know, ideally we could add up a trillion numbers, but hell, is that even ideal? Because after adding up a trillion numbers, there's still numbers beyond a trillion that are in our series. There's numbers beyond the trillionth term that we're going to have to be adding up. So what can we do, though? We can use calculus by saying, okay, I'm not interested in what the first 1,000 numbers add up to. I'm not interested in what the first million numbers add up to. I'm not even interested in what the first trillion numbers add up to. What I'm interested in is taking the limit as the number of numbers goes to infinity. Because you see, if you have an expression for Sn, you can then take a limit as n goes to infinity, and that's not going to give you an estimate for the first 1,000 numbers or the first million numbers. That's going to give you a precise account of what the sum of all the numbers is going to be. So, can we determine the sum of infinitely many numbers? Yes, we can. And the answer is, we keep account of the partial sums, and instead of looking at the first however many numbers, we just take the limit as the number of numbers goes to infinity. And this is like a really powerful way of using our knowledge of the various tactics of calculus in order to wrap our mind around a problem that's seemingly daunting in terms of adding up infinitely many numbers. It really boils down to a single limit, just a limit of the partial sum, a limit of the running tally as number of numbers goes to infinity. Now, since this is a limit, I'd like to recall how every limit can be looked at through the lens of convergence or divergence. So if this limit doesn't exist or is plus or minus infinity, then we will say that our series diverges. Our series diverges if the limit corresponding to its value doesn't exist or is plus or minus infinity. On the other hand, if this limit does exist and is a number from the number line, then we're going to say that that series converges because the limit which establishes the value of the series converges. And really, as we proceed forward in the course, one of the big questions is not just can we determine the sum of the series, but rather, if you're given a particular series, and note, by the way, this series has infinitely many terms in it, so this does not go from I equals 1 to 10 or I equals 1 to 100. This goes from I equals 1 to infinity. This is a series that goes on forever. The question is, if we're given a series, can we determine if the series converges? In other words, if the value of the series is some number on the number line, or if the series diverges, if the value of the series is not defined, or if the value of the series is plus or minus infinity. And the sort of primary tool that we can use in terms of making such an assessment is what we're going to call the divergence test. So the divergence test is essentially looks not at the sum of the terms, but at the terms in this series themselves. So let's look at the individual terms of the series, and if the terms in the series do not approach 0, then I claim the sum must diverge. And actually, let me use an example to sort of demonstrate this. So here is a series. Note, by the way, the terms here, you can see if you took a limit of those terms, you would get 1 because it's an equal heavy rational expression which would have a limit that would be the ratio of the leading coefficients, in this case which would be 1. But now let me actually write out the terms of this series. So if we actually were adding up all of the terms and adding them together, let's see, n equals 1, we get what, 2 over 1 plus 3 over 2 would be what we get when we let n equal 2. n equals 3, we'll get 4 over 3, 5 over 4, 6 over 5, and so on. Now please observe that the terms of this sum do not approach 0. As we've mentioned, the terms approach 1. Now, since the terms approach 1, which you can like physically see, right? Because this first term is 2, and the next one is 1/2, and the next is 1 1/3, and the next is 1 1/4, and the next is 1 1/6. I mean, these terms are getting closer and closer to 1. But since the terms approach a value which is not 0, every time you're adding in something, you're adding something that is nearly 1 in value. And if you add 1 plus 1 plus 1 plus 1 forever, you are definitely going to get something that's infinite. In fact, even if these terms didn't approach 1, even if we took all of these terms and divided them by 2, all the way across, well, yes, we wouldn't be approaching 1, but we'd be approaching 1/2. And even if you approach 1/2, the terms of your series are becoming 1/2 plus 1/2 plus 1/2 plus 1/2. And it doesn't matter how many times you add in 1/2, you're still going to get an infinite value eventually. And so this is some reasoning to support the fact that if the terms of your series do not equal 0, then the sum of your series must diverge. You're going to have a bunch of terms equal to 1/2, add up 1/2 a bunch of times, like infinitely many times. There's nothing you can do about that. That's going to add up to an infinite value. And as a result then, because to sort of echo now back to our goal was to determine if a series converges or diverges, which essentially says, if you are given a series, into what box do you put that series? Do you put it in the box of the divergent series or in the box of the convergent series? Well, depending on what the limit of the partial sums evaluates to, maybe the series' value is infinite, or the series' value is not defined because that limit of the partial sums doesn't exist. Maybe the limit of the partial sums gives you a number off the number line and the series converges. Well, what we've shown down below and sort of alluded to, I guess, in our logic with the divergence test, is that if you take a collection of all the series whose terms do not approach 0, if the terms approach 1 or a half or even an eighth, or hell, if they approach negative an eighth, we could put a negative number, a negative sign in front of all of these terms. As long as the terms do not approach 0, we know where those series go. They're all among the divergent series, because the sums are going to be infinite. So all of these series are among the divergent series, which then sort of begs the question is, well, what if instead of the terms of your series not approaching 0, what if the terms of your series did approach 0? Where do those series go? Oh, it would be all wonderful and nice and peaches and cream if this collection of series would land among the convergent series. And well, while some of them do, some of them don't. So, unfortunately, whenever it comes to this collection, we sort of have to chop this collection into two parts. While when the terms go to 0, some of them are, yes, indeed, convergent. Unfortunately, they aren't all, and other series whose terms whose terms approach 0 are among the divergent series. And really, the bulk of our study for the remainder of this chapter is going to be to sort of wrap our mind around situations where this is occurring, where the terms are approaching 0, and then addressing the question, do we have a series which adds up to a finite value off the number line, or a series that sum is either not defined or infinite. So ultimately, if the terms don't approach 0, straightforward decision, the series must diverge. And that's why we call this the divergence test. On the other hand, if the terms do approach 0, more work is needed to figure out whether or not the series converges.